Welcome. I'm Carl Tape. The topic is Alaska plate tectonics. This is a zoom in of the global maps. So we start with the global view of bathymetry and topography, as well as the plate boundaries. We'll be looking at the plate boundary mostly between Pacific and North America. Here's a geographic map of the region. We have Russia, Alaska, Canada with Yukon, British Columbia, Northwest Territories, Washington and Oregon, giving you some sense of scale for this region. Arctic Ocean, Bering Sea, Pacific Ocean, Gulf of Alaska. And for scale, just a reminder that 1 degree latitude is about 100 kilometers, as we saw. So we don't really need a scale bar. We could look here and see 5 degrees. That's approximately 500 kilometers shown here. Topography of the region, the highest point is Denali. It's in Alaska right here at 6,190 meters above sea level. The highest coastal mountains in the world are the St. Elias Mountains, right in this region. And these are formed by collision between a thickened chunk of the Pacific plate known as the Yakutat Block with North America forming these mountains. As always, there's a lot of interesting features in the bathymetry. First, the deepest regions are along the Aleutian-Alaska Trench. This is marking the subduction of the Pacific plate beneath North America. It reaches a depth of 8,100 meters right around here, and that is deeper than Denali is tall. Alaska is even bigger than it appears if you consider this continental margin, and this feature here known as Beringia is a reminder that in the past, times when the sea level was lower, these were possible pathways for human migration that were exposed to land. Here we see the topography and bathymetry together. We can, no borders, no coastlines. This is the way to look at the region and ask the question, how did these features, these mountain ranges, these trenches, these seamounts, how did these features get to where they are today? There's a tectonic story related with everything, and that's part of the joy of studying this region. So here we have the big picture, Pacific plate, North America plate. We also have the Juan de Fuca plate here, where new material is being created at this spreading ridge. There are thousands of earthquakes in Alaska. This shows a subset of the largest ones. These were the magnitude greater than 5.5 over the past 50 years. We can see that earthquakes mostly follow the plate boundaries. They are offset from the boundary here as they are everywhere in the globe. This is related to the fact that most of these are occurring within the plate as it goes down and away from the upper plate. So this is most of these are actually in the Pacific plate underneath that we see here. We also see some earthquakes along this eastern boundary associated with strike slip motion here. So we're interested in studying earthquakes in 3 settings: the Aleutian-Alaska subduction zone, seeing this arc of dots paralleling the plate boundary, and also the strike slip. The Queen Charlotte strike slip fault is essentially the northern San Andreas fault. Same kind of motion, right lateral strike slip motion. Third is intraplate, meaning inside the plate or within the plate. So we see some dots, scattered dots out here. When we look at smaller events, though, as we'll see next, there are tons of events, tons of earthquakes in Alaska. This is showing the colored dark ones are the deeper ones, the yellow ones are less deep, and the red ones are shallow. Again, here are the 3 different settings. Subduction zone here, that's the dominant earthquake maker in Alaska. Strike slip faults and these events here on this plate boundary. And then also all these events happening in interior Alaska. So we're right here in Fairbanks, right in the center part of this intraplate earthquake activity, and almost kind of related also to subduction as well, where the Pacific plate extends deep under central Alaska. There are lots of active volcanoes here. Active means they erupted during the Holocene, the past 12,000 years. If you look at the Alaska Volcano Observatory website, you'll get a much more color-coded description of what's actually erupting today. So different meanings of activity in terms of planes flying overhead into potential ash clouds. That's different from a geological characterization of this region. And so here we're looking at anything erupted in the last 12,000 years. You can see this really beautifully systematic volcanic arc that is along the subduction zone here. We're interested in volcanoes in two settings. One is the subduction zone. There's one here, but there's also the Cascadia subduction zone in Washington and Oregon. And this is associated with this Juan de Fuca plate subducting to the east under that region. So this is a second subduction zone. And we're also interested in volcanoes in the region from spreading, rifting, or divergent. So here we have volcanoes, right on the spreading between the Juan de Fuca plate and the Pacific plate. And these arrows are just pointing them out. These are not plate motion arrows as we've seen before. There are two hotspots, both on the Pacific plate, the Bowie and Cobb hotspot. We'll look at these in a little more detail now. So the hotspot tracks, which is the line of seamounts, point in the direction of plate motion from the youngest volcano to the oldest. So here shows these hotspot tracks in the direction pointing from the youngest to oldest, and that's the motion of the Pacific plate. We can zoom in a little bit for the Bowie hotspot seen here. You zoom in, you can see these seamounts, or basically best thought of as ancient volcanoes or previously active volcanoes, with the most active one right here. This shows the snapshot from the plate motion model, and we can see, as we might expect, it's not necessarily perfect agreement aligned, but taken together, we can see this motion is roughly aligned with the direction of these hotspot tracks. There's a detailed study in 1985 looking at all these different seamounts, dating them, and trying to think about the relationship and how they formed with respect to the spreading ridge and also the motion of the plates. And so here we see the Bowie seamount, and the Cobb seamount is right here, but it's the Cobb hotspot is actually now on the spreading ridge as shown here. Hotspot track direction is giving us youngest to oldest seamounts, and that is the direction of plate motion. We zoom in on the Cobb hotspot. Further to the south, here's the Juan de Fuca plate. This shows some of the sense of humor of these geophysicists. The seamounts seem to be named corn cob pipe. We also see this word axial, and so this is the youngest one that's on the ridge now. But so the Cobb hotspot, Cobb isn't the youngest one, but it's named for this prominent one. So normally we've looked at activity on the surface of the Earth, and we haven't really dived deep. In the depth, the diving deep gives us some idea of the process, but this was a figure from a paper that really warranted showing here because it nicely conveys this relationship between the plate motion and the hotspot tracks, and even in this case, a spreading ridge. So this is for the Cobb hotspot. Started out on the Pacific plate. The authors have shown an interpretation for it 8 million years, 6 million years, 4, 2, and present day. At the present day, you have this A for the axial seamount, where it's actually aligned with the spreading ridge. So it's kind of easier to understand in the past. At 8 million years ago, here's the spreading ridge off to the side. Here's the hotspot, and we see this Eichelberg submarine volcano would have been active at this time, formed on the Pacific plate on top of the hotspot. And as time has gone on, the ridge the ridge is also moving with respect to hotspots. You can see it getting closer and closer. And here a couple million years ago, we can see at the Cobb hotspot had been, seamount had been formed. And today we see that the axial seamount and the ridge are aligned. So we get an idea that as the authors have drawn this sketch, the reference frame is the hotspot reference frame. The hotspot in every panel is fixed, and the ridge and these seamounts are moving on top of them. Here's a simplest comparison between earthquake locations and active volcanoes. We can see really good correspondence along the subduction zone. We can see, yes, there's a systematic offset that we expect. The dots are associated with the plate that's going down, deformation mostly in the Pacific plate, and the arc volcanoes form a certain distance away from the trench. We can think of hotspots as volcanoes. They do not all appear in the active database of volcanoes because they have not erupted within the last 12,000 years or the Holocene. We do see with Cobb, the hotspot is right on active volcanoes, whereas with Bowie, there hasn't been, a Holocene eruption, so there's no black triangle in there. The age of the seafloor provides us with insights into the style of some of the plate boundaries and especially the spreading ridge. So red means brand new oceanic floor is being created here at the Juan de Fuca spreading ridge. And that some of that goes to the northwest, some of that goes to the east. And so what we'll look at here is that along the Aleutian Alaska subduction zone, we see that the age of the plate gets older from the east, the yellow at 35 million years or so. Subduction goes along here into the greens, to the west at about 90 million years. This oceanic plate material formed at this Juan de Fuca ridge, which today creates new or 0 million year old material. So this ridge is creating seafloor, sending it on its way toward the northwest to be destroyed and consumed at the Aleutian Alaska subduction zone, or your other option is to go east and get consumed or subducted underneath Washington and Oregon as part of the Cascadia subduction zone. So it's good to look at this seafloor. We can think about, this spreading plate boundary is the dominant feature, but then we can also think about the age of the seafloor as it goes down. The plate motions help us think about the different types of plate boundaries in this region. So here we're zooming in to the motion. This is the Pacific plate, North America plate, and we can see here also the Juan de Fuca plate. In some cases, it may be helpful to think about the plate motions with respect to fixed North America, as shown here in white. For example, here, it is clear that the Pacific plate converges toward Alaska at about 60 millimeters per year. That's shown in the green. And in the east, along this Queen Charlotte Fairweather strike slip boundary, it moves parallel to southeastern Alaska. So if I'm standing in southeastern Alaska looking out toward the Pacific, I see the Pacific plate moving to the right. That's what makes it a right lateral strike slip boundary. And of course, here we see, if we're in Oregon and Washington, we see the convergence of the Juan de Fuca plate associated with subduction. But in most cases, we will think about plate motions with respect to hotspots as shown here. In this region, the Pacific plate moves to the northwest at about 60 millimeters per year. The North America plate moves slowly southward at about 10 millimeters per year. Convergent motion occurs along the Aleutian Alaska subduction zone as expected. Right lateral strike slip motion occurs along the Queen Charlotte strike slip fault. And to pull this all together, the perspective we showed in the opening lecture, we see this oblique view of Alaska on its side. This would be Fairbanks right here, Anchorage. And we're looking at the Pacific plate subducting under North America. So along this margin, it moves side by side. This is the Queen Charlotte Fairweather strike slip fault system. We can see that as it goes under, we have this arc of volcanoes being shown here, and the contact is where these great large earthquakes are created. So just as a reminder, we have this Latin root of sub, under, duct, lead. So subduct meaning to lead under. And this is the picture we want to keep coming back to and thinking about earthquakes in Alaska and really the origin of some of the spectacular features, mountain ranges, trenches, all that we have. Takeaway topics. The two main types of plate boundaries are subduction, Aleutian Alaska, and right lateral strike slip, Queen Charlotte or Fairweather. There's also a collisional zone that forms the St. Elias Mountains, the largest coastal mountains in the world. The Bowie and Cobb hotspot tracks reveal Pacific plate motion to the northwest. The Pacific plate moves to the northwest at about 60 millimeters per year, and the North America plate moves slowly southward at about 10 millimeters per year.